Well, lecture attendance is dwindling. We've got just over a third, maybe 35% attendance, which is not that great, to put it mildly. Now, one thing I am worried about is I took a look at what people had pushed to GitHub, and we've got a programming assignment due next Friday, and I see 9 repositories that have actually pushed any changes to emulate.c, and only 6 that have pushed any changes to test.c. It's not an especially difficult assignment, but it's one that is probably best not left to the last night. It would be really useful if you could, you might find it. Damn, there's something about some of the chalk. Anyway, you might find it really useful being able to ask for help after you've started on it. And if you start on it next Thursday or Friday, that's probably not going to be possible. So is there anything that's been blocking anyone from getting started on the programming assignment? Is there anyone who hasn't been able to clone the repository from GitHub? All right, how many of you haven't cloned the repository from GitHub yet? Okay, please do it today. Take a look at the code, and perhaps I'm regretting not assigning a lab 0 or programming assignment 0, which is just basically clone this repository, create a file that says I did it, and check it back in, and maybe 1 or 2 other things. But it's the time to get any issues with that solved is this week, not next week. All right, so let me back up and address a couple of high-level class things. Okay, there's there's 10 homeworks, 10 short homeworks, and I've mentioned it before, but I'll mention it again. People ask me what the questions on the exams are going to be like. The questions on the short homeworks are stolen from the exams. They're extended somewhat, and maybe more, an additional part or 2 added because you can spend more time on it. But for both the midterm and the final, the questions you see should be familiar to you because you'll have seen something like that in one of the homeworks. We've been covering, let's see. So the outline, which will hopefully make it onto the website and Canvas, or onto the website soon, is okay. This takes us up, you know, maybe 4 or 5 lectures past March, or 3 or 4 lectures past March break. I don't have the rest of the spring schedule, at the top of my head, but the the programming assignments are, well, oh, so this is what the semesters, you know, um, so the last part of the semester will be I/O and file systems, and then a smattering of stuff. Oh, and we'll talk about virtual machines and containers. So the assignments are, the CPU simulator you're working on now, or emulator, a very simple shell, a simple thread library, and a file system. And I believe that, I've got to double check, but I think that each of these programming assignments can be solved in like 200 lines or less. Granted, that's maybe after taking a 300-line solution that works and staring at it for a while. But they are conceptually harder than the actual implementation. And finally, I would ask that on these programming assignments, everyone please try to start with a simple implementation of one part of it first. And in general, I'll try to, I'll try to suggest ones to start out with, and then add features to it. So for the first programming assignment, it's very straightforward. Basically, it's going to be tested an instruction at a time, and you're implementing it an instruction at a time. So if you can look at the test.c file, that's testing 2 different instructions. Maybe you implement the first instruction tested, and then implement the second one. Or you could pick a simpler instruction like set, which I believe is the first one in the grading tests on Gradescope, and write a test for it and put it at the top. But in general, your life will be much more difficult if you try to write your entire solution and then you try to debug it. Because if you are always going from working code to working code, then and making relatively small changes, then it's very straightforward to figure out where you introduced an error. It's obviously in the last few lines that you changed. In each of these cases, you're given a skeleton framework that has, working code in the sense that, for instance, you're given an emulate function which doesn't do anything. If you, you can, it will actually, you can actually submit that and run the Gradescope tests on it. It runs its working code in the sense that it will, compile, run, and fail every test. So then you change it to something which will compile and run and pass one of the tests, and then two, and so on. So, all right. So in the last lecture, I introduced the concept of I/O virtualization. So in particular, assuming that we had a language with higher level interfaces and inheritance, that if we have this class here, then so we could have, and then similarly, and finally, So we can have a file table of objects of this type, this 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 interface, and then and then just invoke the read method of whatever this entry points to. Obviously, we've got to check and make sure that the file descriptor is valid. It's within the range of open file descriptors, and the pointer in there isn't null. But essentially, this is why Unix uses small integers for file descriptors, because there quite literally is a table in the operating system, and each entry in it is a pointer to an object of, that's basically of a certain, that implements this interface: read, write, close, a few other things. They don't implement open because open has to be fancy. Open has to look at the name and figure out which of the different types of things it should be opening. Is it a network connection? Is it something else? But this is why you're able to use the read or write system calls, no matter whether you're reading from the terminal, you're writing to a file, or reading from a file, or you're operating on a network connection. In each case, the read system call doesn't care. It just looks up the specific instance in the OS and calls the read method or the write method. And we trust that when we opened a file or device or something, or created a connection, that the correct internal object instance was created and put into this table. All right. Now we're going to talk more about processes. So a process is basically a running program. And in fact, a process is what you've used as in your programming to date. In other words, you're not programming the computer itself. You're not programming the hardware. You're not writing code that fiddles with, keyboard drivers and frame buffers and disk controllers, because, you might finish the USB driver by the time you graduate, but, then you've got to display stuff to the screen. What the process gives your code is this very simple fake machine. It executes all the CPU instructions, and then it doesn't have any, nasty hardware. It doesn't have any hardware that you have to, figure out how to program it and so on. Instead, it has system calls, and those system calls let you work with hardware at a much higher level. So instead of setting registers and disk controller to get, to tell it the numeric disk block you want, you have an open system call that you can pass a readable file name. Instead of reading and writing packets from the network interface and trying to implement TCP by yourself, you have a system call that, a connect system call that lets you, take a socket, a connection object that you've already allocated and connect it to, a destination, after which you can do reads and writes. So now, normally when we talk about a virtual machine, a VM on your laptop, that's one that's actually pretending to be, a real hardware machine. The thing about the process virtual machine is that it's simpler than the real hardware. That's the whole point of it. It's something that, you can write a program for without, studying hardware manuals and being an expert on I/O systems. And then the operating system and the device drivers translate these high-level system calls into the operations on the hardware underneath. Using, basically the mechanism I've described here. It's just, elaborate this until it's, a million lines of code for, 100 different devices or more, and, and you have a real modern system. It would actually be nice to teach this class with like a 30-year-old operating system, but it's actually because it would be so much smaller, but it's so hard to get anything to run on that, any of the modern tools to run on that, so we don't. Okay, now the thing is that one reason that the operating system supports processes, or one of the things it does with this process abstraction, is it supports multiple processes. So you can have two processes running at the same time on your computer, and and it's not just because your computer has multiple cores. Even a simple computer with a single core CPU supports multiple processes. And if you look under activity manager, activity monitor on the Mac, or process, I forget what it is, in Windows, you'll see that there's probably hundreds of processes running on your laptop when it probably has no more than 4 or 8 cores. So what the OS is doing is pretending that each process gets a CPU, but it's actually switching back and forth between these processes because most of them aren't doing very much. On your Mac, those icons up on the top right in the, in the top bar, in the menu bar, there's a process associated with each one of them. Despite the fact that all it does is, for a lot of them is remind you that you installed something like Adobe Creative Cloud that you haven't gotten around to uninstalling yet. And the, so every so often, maybe every second or so, the OS might switch to that process, and it goes and checks and says, I still don't have anything to do. Or, in fact, the process might have called into a system call saying, give me, send me some input. Maybe it was on a network connection, maybe it was something else. And in that case, the OS is never going to switch to that process until some input actually comes in. So there's usually plenty of CPU, even with a single core, to handle a bunch of processes because most of them don't use much. But the problem is switching from one to the other. Okay. You know what? This really needs a full board. Okay. So we'll spend some more time talking about this later when we talk about multi-threading, but let's see. Oh. God, I hate that. Okay, so in previous lectures, I talked about the way we use the stack and the stack pointer to save the state of a function. That basically the current state of your program is located in, basically 99% of the current state of your program is on the stack. That's saving where you are in the computation. You called, function A called function B at this line, and function B called function C, and so on. And so the specific point in the computation is saved by all those return addresses on the stack. And all of your arguments and local variables are stored on the stack. The only things that aren't on the stack are globals and our globals and operating system state. But in particular, what if we could make a function okay, imagine you have your code and it calls a function yield, which just goes and, sits in a loop for 1 second. Now, and then we have a different yield function that instead of spinning in a loop for a second, it switches stack pointers. So we've called into yield 2, and it temporarily says, let's change the stack pointer to here, and then do a return, and now we'll be running process 2 code for a while, or process B, and then eventually process B is going to call yield again, and now we're going to set the stack pointer back to here, and finally we can return back to process 1. So basically, we're pretending to process 1 that all we're doing in this yield is like waiting for a second, but in fact, we're switching to a different process and running that process for a while and then switching back.
Are we waiting to go back to A because of something that pops up in B, or do we have an actual timer that is waiting for 1 real second?
Well,
is it just an arbitrary amount of time?
In this case, in the simple case I'm explaining, we're not going to return from B until B calls the yield function. And if B forgets to do that, we're out of luck. Yeah. I'll talk some more about ways that the OS can make that more reliable, because, at that point, honestly, one of the nice things about having multiple processes run on a computer is that if one of them crashes, the computer doesn't go down. I described how with MS-DOS, you basically have an operating system that reads a command from the keyboard, loads the program into memory, and then jumps to the program. And that program is the only thing running on the computer. And if that program goes into an infinite loop, then the computer just sits there unresponsive. And that's why they had the Control-Alt-Delete mechanism, so that you didn't wear out your power cord by repeatedly unplugging the machine from the wall. So here we've managed to get 2 processes running, but we'll need to add a lot more because, we're still at the mercy of each of them being implemented correctly. And in general, requiring all the software on your computer to be bug-free is not the best strategy. We'd like something that can recover from crashes rather than, that you have to recover the system from them. So let's see. Okay, this isn't very readable. Um, oh, that's going to suck. Okay, what's happening is we've got the real stack pointer. This is a register in the CPU, and it's pointing into process A's stack because A is running. We're calling things and returning and storing local variables there and doing all the stack-like things that we do. But in this yield function, we're going to do a very simple trick. We're going to store the stack pointer into here. And we're going to load the stack pointer from here. So now the real stack pointer is pointing into process 2's stack. And this return statement returns to whoever called this function in process B. And this is where the the CPU is being, this is where it's easy to think that the CPU is smarter than it is. The return instruction has no idea what, where a function was called from or anything like that. All that it does is look on the stack, pop an address, and jump to it. So if we do something crazy like change the stack pointer, normally if we did that in a regular function, it would just be a really bad idea. We'd crash. But for this specific purpose, we can change the stack pointer specifically to point to the stack of a different process and then return into that process. And then later on, this process will be running and it will call yield, and that will switch back here. Obviously the yield has to be a bit more complex than this because this yield will only ever switch from process A to process B. We'd rather not have a separate function for each, we'd rather not have a different function for switch from process B to process A. And then, once we start adding more processes than that, but I'd rather not put a nice general function on the board here. But the point being that all that either of these processes see is that they called into a yield function and some time went past and eventually that function returned. They have no visibility into the fact that, while they were sleeping, the CPU took on an alternate personality and was running around as process B. Or when B called yield, it was running around as process A. And because these have separate stacks, and I hope they have separate global variable spaces, and since the OS is doing the switching, we can add some more, obviously this isn't going to be 3 assembler lines, but we can also switch between different file tables. So each of them has a separate OS state, and each of them will be able to run a full-fledged program on it by itself without having to know that the other process is running. Now, the main problem here is that this requires each of the processes to call yield from time to time to give the CPU up. There's a couple ways we deal with this. It turns out that the two processes probably don't know most of the times that they're calling yield, because whenever they call an operating system function, like if they do printf and that calls write to, put the output on the terminal, the OS might decide, oh, you've been running long enough, I'm going to call yield and let another process run. So the OS can do it anytime, it can tack a yield, it can add a yield to any of its own functions. And so whenever one of the processes, tries to print an output or get input or read a file, that's an opportunity for the OS to say, how long have you been running? Maybe it's time to switch to another one. It turns out that there's another mechanism called interrupts that let us do this as well. Well, that's the last that I try those colored chalks. Maybe some different ones. So what an interrupt is, so okay, backing up. We know what the call instruction does. When the CPU executes a call instruction, it's going to push a return address on the stack, and then it's going to jump to a location. Now, interrupts are sort of like forced function calls. So, let's say we put a little button here. That's a terrible, I'm not even going to try and draw someone's hand. But someone presses this button, and what the CPU does is after the current instruction finishes, instead of executing the next instruction, it forces a function call to a predetermined address. So on a really simple CPU, this address might be, predetermined. Maybe it's address 0 or 100 hex or something. You read the data sheet and it tells you where, where this interrupt table goes. On a more complex CPU, there's probably a configuration register somewhere that has an address that specifies, how interrupts should be handled. But the key thing is that, this is making that hard to read. Our CPU was happily executing instructions, and then a real world input came in and told it to insert a function call in the middle of our program. So the code that we wrote has no control over this. There's this wire coming in, and when that goes high or low or whatever, the CPU will force this function call as the next, as the next instruction. And then at the end of this instruction handler, it will return back, and we'll have no idea that this happened. In fact, if there's an instruction on the Intel CPU, I'm not sure what it is on the Apple Silicon, that lets you read a fine-grained time counter, and you can sit in a loop and see how much time passes between executions of the loop, which is going to be a small number of nanoseconds each time. And then every once in a while, you'll see a gap of a microsecond, 10 microseconds, maybe a millisecond. And that's not because of anything your program did. Your program's sitting there in a loop. Instead, what happened is there was an interrupt, and processing that interrupt took time. Maybe it was because a network packet came in and the operating system had to do something with it. Maybe it was a key press. It turns out, for our purposes, the simplest type of interrupt is what's called the timer interrupt. And so this is a really simple device that's either in the CPU or next to it on the motherboard, that all it does is you configure it to every so often just interrupt the CPU. It's basically a clock tick. Um, on Linux, I forget if it runs at 256 a second now, or 1,000 times a second. It used to run at like 100 times a second, and you can use it for a number of things. Basically, it's how the operating system can keep track of time, because the operating system, most of the time, the operating system isn't running. Your code is running. It's not until you do a system call, for instance, that the OS starts running anything. So what this timer interrupt does is it basically, this interrupt handler is part of the OS, and so it lets this piece of code run periodically. The simplest thing it can do is just increment a counter, and that gives the CPU a clock so it can tell what time it is. But the other thing it can do is it can check and see how long your process has been running. And if it decides that it's been running long enough, then it can call this yield function and switch to another process. And then eventually someone will switch back to our process, and that interrupt function will return back, and we will happily go on our way, not knowing that in between two instructions, the CPU basically took a vacation on us. Unless, if it was in a tight loop looking at the timestamp counter, then we'd notice, that suddenly the CPU got stolen for, 10 milliseconds or something. But otherwise, we'd have no way of knowing, because it doesn't affect our code. It just means that we were executing, a billion instructions a second, one instruction in 10 milliseconds, and then back to, the original billion instructions a second. But our code doesn't know that there was a delay between two lines of it. So that's what an interrupt is. It's just a forced function call. Various types of interrupts will force the CPU to make a function call to different interrupt handler addresses, depending on the type of interrupt. Yes?
So like in the two process examples, if like process B didn't end up calling like the yield function, then the timer interrupt would be able to like notice, oh, this process has been going on for too long. Like,
yes. Yes. Each time, one of the things the timer interrupt does is run, in Linux, the function's called schedule. It's the scheduler that, basically is going to say, have you been running long enough for now? And if not, don't do anything, just return. If so, then, do this context switch. Save the stack pointer, load a new stack pointer, and return. This this sort of trickery is, it's one of the things. We're not going to write this code ourselves in this class. For the thread assignment, I give you some debug code that you can call that does that, because part of the process of making CPUs faster over time is making it more difficult to do this stuff. But also because in general, programmers and compilers aren't used to things like local variables going away because we switched from one process to another. And so, um, anyway. So I guess what I mean is conceptually, this is what's happening. We're switching from one process to another. And in general, someone writes the code to do that once, and um, you know, and you use it until and then everybody uses that. That's actually one of the things. Yes.
When you switch processes, how does it know what to send the program counter to?
You load the stack pointer for the new stack, and then you return. So while you're doing the switch, the program counter is in this yield function. And then when we return from yield, because we've switched the stack pointer, we're going to return somewhere else. So basically what's happening is so we call into yield, if this is, and yield returns to a different thread. Now, there's a chicken and egg problem here because this only works if the second thread has already called into yield and is waiting there. It turns out that we basically have to fake things to get a process started out. We have to set up the stack so it looks like they called yield, and that way when we switch to it, it returns to the right place. So the first time it's going to return to main. And then each time it calls yield, that yield is going to return somewhere else. And then eventually someone else will call yield and it'll return back to us. It's very counterintuitive. Worse yet, it seems like it's sort of constant difficulty because the more you study programming, the more you burn into your brain this model of the function abstraction and how functions work. And so that in turn makes it harder to understand this, this context switch idea where you have something that's totally breaking that function abstraction. You're calling into a function and it's returning to somewhere else. So basically, the more you know about programming, the harder it is to understand the context switch, which is a pain, but it's what it is. The key thing, though, is that it gives us a way to switch back and forth between multiple running programs without the programs being aware of each other. You don't have to write one big program that does everything that's on your computer. that's watching all the things on your screen, that's implementing the web browser and the text editor and, I don't know what else, all the other apps. Instead, each of them can be a separate program running on its own and, blissfully unaware of what else is running on the machine, except for, I guess that's it. The program will always be unaware. The user may eventually notice that things are slow if there's a lot of processes running, but the code itself doesn't have any idea how long it's taking. Only the user does. All right. So now that I've explained sort of at the low level how switching between processes works, I'm going to talk about the high level API that we have in Unix for dealing with processes. Because, I'm going to skip over, I'm skipping over the details of how under the hood of how you create a process, because, you can understand the concept of stack switching without worrying too much about how you get it started. But I want to talk about the APIs that Unix uses to create new processes, in particular because normally the way Unix works is, the way the command line works, for instance, you've got this shell which basically the shell is just the shell is basically creating a process and then waiting for it to finish. So if you type ls into the shell and return, it's going to create a new process, and that process is going to run the ls executable, and meanwhile the shell is going to wait until it's done. It's not like MS-DOS. It's not loading the program into its own memory. It's not calling it. It's instead creating a whole new process, and that process is going to run the command. So okay, in Unix, for various reasons, historical reasons, the way you create a process is by duplicating the current one. So the parent is happily going along, executing your code. It calls fork. And fork returns, but it also returns in the child process. In other words, fork is a function which returns twice, which is you call it once and it returns twice. That's hard to wrap your head around. The idea is that it returns once in the parent and once in the child, and that child process is an exact duplicate of the parent. The operating system copied the entire memory space, everything else, into that child process, and set its stack pointer and everything so that when it returned, it would return from fork to the same place that it returned in the parent. It's just you know that you're in the child because in the parent, we get the process ID of the child process. And in the child, we get a 0, which is an illegal value for that. So once again, we're doing this thing where we distinguish, the space of possible things. Here, 0 is not a legal process ID, which that's probably driven by this interface here. So we'll have code, the next line or two below this is going to be saying if ID equals 0, do child process things. If ID is 1, do parent process things. So in particular, a classic parent process thing to do is to wait until that child is finished. That's what the shell does, at least a simple shell that doesn't have, that doesn't let you do things in the background and stuff, because, that's the whole idea is you want, when you type return, you want the program to run. You don't want it to start running and then sit there spewing output while you're typing additional things in the terminal. You want it to wait. You don't want to give another command until that program's done. Now, the classic thing to do in the child is so, in a shell, for instance, in the child, what we're going to do, maybe after a couple of lines of code, is we're going to use the exec system call. So I'm going to underline, these are the 3 system calls we've got here. The exec system call executes a program, and what that means is it goes and reads an executable file and replaces everything in memory with the program that it got from that file. And at that point, this is now, from this point on, our original, if this was a shell, up through here, we're still running code in the shell because we copied the entire process. And that means not just like variables and things like that, but the code as well, and the position in the code that we were at. So, our program kept running. Basically, we cloned our process, so we had 2 copies of it running. And then the child copy said, replace everything with this program and start running the main function of that program. there's in Windows, in contrast, if you want to create another process, the standard system call basically says, create a process with this program and these arguments and give me a handle to it. Instead, you do it from the inside in Unix. You clone yourself, and then you do the system call to basically replace yourself with that program. And and that includes command line arguments and so on. I'm not going to argue which approach is better. It turns out recently big machines have run into well, never mind. But we're working with Unix, and so that's the way it works. Now, I mentioned that we might want to do something before we call exec here. And in particular, a key thing with the Unix shell is the ability to do I/O redirection and to be able to do it in a uniform fashion for every program. And the way we do that is, I mentioned this concept of a file table. In every Unix process, there's 3 file descriptors that are predefined when the process starts. Standard in is 0, standard out is 1, standard error is 2. We'll forget about standard error for now. But the output of when you put a printf in your program, whatever data you have gets formatted, and then it gets written via a write to file descriptor 1, because printf goes to standard out, and standard out is file descriptor 1. It doesn't need to open any files or anything like that, because Unix guarantees that when your main function begins executing, file descriptor 1 will be standard out and 0 will be standard in. Now, that means that, and if we wanted to redirect the output, it's easy to describe what needs to happen internally. We need to make file descriptor 1 point to file.out. But, in the program, in your own programs, in the shell, for instance, which is just another program, there's nothing privileged about it. It doesn't have any access to these internals here, all it has is a set of system calls that let it do things like open files and close them and read and write them and so on. So how do we actually accomplish this redirection? Well, okay, first we can so this is going to be on the child side of our shell. We can open the file that we want to redirect output to, and that's probably going to return file descriptor 3. For the sake of this, I'll assume it does, because that's usually the next free file descriptor, and for various reasons, Linux tends to allocate them in order. Now, so A established this mapping, that file descriptor, let's say it's 3, is referring to file.out. Now, this oddly named call is going to close file descriptor 1, so get rid of its association with the terminal, and copy the link in entry 3 into 1. So now both file descriptors 1 and file descriptors 3, if you wrote to either of them, they would write to file.out. And then finally, we're going to close this file descriptor, and now we have the redirected state we want, where the input is coming from the terminal and the output is going to file.out. And so now and the reason this works for every program is because we've mandated that, that's how standard input and standard output works. That standard output is writing to file descriptor 1. And where does that go? Well, wherever file descriptor 1 was pointed to when your main function starts executing. And so, after we do this, this little shuffle here, our redirection is done. And now we can call exec, and and whatever program we're executing will see standard out directed to this file. So that's how I/O redirection in Unix works. It's a matter of, like I said, there's 3 entries in the file table that are always there. Or if they're closed, it's because, sometimes a process gets run with no standard input, for instance. There's system daemons that run that way. Well, that means something will close this before it starts running the process. But, because they were meant to be. But basically, these 3 entries are given to the process. It's, input, output, and then error. So in particular, error is where, if you have a program that you typically, produces a lot of output, and you typically redirect the output, well, if something's wrong, you would probably print something to standard error before exiting, and that way the user will see that error message even if they redirected the output. But that's the last I'll say about standard error for at least the next few lectures. But the point is that I/O redirection works because programs take these input and output entries as given when they start. They don't control where their input and output point themselves. Instead, it gets set up for them by the shell. And so, in the shell, we clone it ourselves to create a subprocess. We do some I/O redirection if necessary, and then we execute that program. So let me think. I guess this would be a good time to ask for questions, because I think there's probably a good number of parts of this that aren't clear, and so I can try and reiterate some of the more confusing parts and see if it helps. Anything that you'd like me to explain, try to explain again? Yes.
Can you go over the difference between fork and exec? You mentioned that fork begins the process, but exec begins the program.
Yes. Okay. Okay, so maybe a good way to explain it. What fork does is, okay, let's imagine this program. It's just going to loop 10, 20 times, printing a number, and then sleeping for 1 second. If I put this line here, so the original program would print and so on. if I put this line here, then what we're going to see is basically we made a copy, we cloned ourselves at this point, and now the two clones are both running. But what's running is it's two clones of our original program. That's the thing. In fact, the system call, the underlying function, function in the Linux kernel is called clone that does this. It's making a duplicate of the current process, and now instead of one process running this code here, we have two processes running it. And so each of them is going to print out a string of numbers, and they'll probably be nicely interleaved, but at least with a sleep this long. But it's not changing what program is running. Yes.
If you put another fork there, would you end up with 3 or 4?
If you just put it here, you'd end up with 4, because each of these would end up splitting. In fact, if you put a whole bunch of calls to fork in a row, you get a particular denial of service attack called a fork bomb, which I think modern versions of Linux are protected against, but certainly 20 years ago would, I seem to recall that the only way to recover from it was to power cycle your machine. Yes.
If you didn't have the sleep call, would it just be printing like 1, 2, 3, 4, and like that twice?
Well, the reason for this is because if you didn't have the sleep call, then it would probably run this one for a burst and then this one for a burst, and those bursts would probably be able to print, hundreds of, much more than a blackboard full of because the OS would be giving each a time slice of 10 milliseconds, 100 milliseconds, whatever, before switching between them. If you're sleeping a second, then you'll get a nice, pretty output like this. Now, normally in a shell-like situation, you would check this ID and do one thing in one branch and one in the other. And in particular, in the child branch, you would use the exec system call, which is basically says, I want to execute that program, not the program I'm currently running. So the fork system call returns twice, one in the parent and one in the child. The exec system call does not return because it loads a new program into memory and then calls the main function of that new program. The only time this returns is with an error code saying, no such file or directory, or you don't have permissions or what.
To denote that we only want you to do this in the child process, if ID equals whatever.
Yes. I mean, you could do it in there's nothing preventing you from doing it in the parent process, but that wouldn't be a shell. That would be something else. Other questions? Yes.
Is the reason for the redirection from one pointing to file that out just because all the processes assume that standard out is at 1 and you can't just use
Yeah, there's no way to tell the the new program. We can't tell the program use file descriptor 3 for your output because we've predefined that file descriptor 1 is the output, which means, which in a way is, it means that that's always going to work, because as long as you set it up so that 1 is pointing to the right place, that output will be redirected. Um, whether there's, um, you know, there may be, this is a very Unix-like way of doing things. Windows has a much different philosophy in all of its APIs. But, um, but yes, because we've defined 0 to be in and 1 to be out, it means we need to do this dance to take the file descriptor pointing to file that out and move it over to, so file descriptor 1 is pointing to, using that dupe function. And I think, and you can look at the manual, the instruction. So you can look at the documentation for dupe 2, but this diagram here is probably going to do a better idea of explaining, because it's going to talk about file descriptors and file descriptions and this and that. But the key thing is that there's this thing, which is, the internal OS representation of writing to file .out. And we had 3 pointing to it, and we need to get 1 pointing to it, and then we want to stop 3 from pointing to it. And so this is how we got 1 pointing to it, and this is how we stopped 3 from pointing to it. All right. Any last questions? I'll finish up then. And oh yes.
Yeah, sorry, just really quick. So after you finish writing the file that out, I guess you would have to redirect get back to the terminal.
No, because if we do this in the child process, then all the stuff we did is going to go away when the process finishes and calls exit. So it turns out, for a lot of programs, exit cures a lot of sins. If you have memory leaks, well, then you exit. If you have open file descriptors, well, you exit and they're gone, and so on. So yes, in the second assignment, you'll be implementing redirection, and that's one key, thing to make sure that you redirect, your child's output and not the shell's output. We don't want the command prompt showing up in that file.out, when you're prompting the user for another, for the next command. Yes.
So is that one of the reasons we like the child process there? Is because it's very easy to almost reset?
Well, it means that I guess one way to look at it is, we're creating a separate process for the command so that it's just a normal command, so that it's a program and the shell is a program. And if you think about the pipeline idea, in fact, that's where, having child processes is important, because now we can just create 2 child processes. And, I'll talk later about how, the pipe, there's a pipe API for, that again, gives you file descriptors to write to and read from, that the shell can hook those together. But, that way each command is running in its own little world, and the shell is just babysitting them from afar. It's calling wait, and to wait until they're done. All right, that'll be all.